Alright, moving on. Question 4. So question 4 states a hole is punched in a full milk carton 6 centimeters below the top. What is the initial velocity of outflow? Repeat that question. A hole is punched in a full milk carton 6 centimeters below the top. What is the initial velocity of outflow? So we got this milk carton that can be approximated to this shape right here, I guess. And so there's a hole punched 6 centimeters below the top. So this is the top, 6 centimeters below the top. So somewhere around here, say. We don't know how long this milk carton is. We have no clue. It's not given to us. A hole's punched, and so we'd expect milk to drip out that way, right? Now what? What is the initial velocity of outflow? So how fast is milk flowing out, or outflow, right? How fast is the milk jetting out from the hole that we just punched in? So the idea that we want to use from now for such questions is Bernoulli's equation. It's kind of, I wouldn't say it's equivalent, but it's very similar to the conservation of energy equations we've had in chapter 5 and 6, where we would say the sum total of potential plus kinetic energies initial is equal to final, or the sum total of all energies is conserved, assuming there's no non-conservative forces like friction involved, right? So the same idea here. We need an initial and a final. First of all, what does Bernoulli's equation look like? It says pressure plus half density velocity squared plus density g times h is a constant, or is conserved, or also could be said that initial equals final. So the pressure plus half density velocity squared plus density gh initial equals the same final. The sum of all of them would be the same, initial and final. You do have to note the difference between this density rho that I draw here and the P for pressure, right? They're two different letters. One's Greek, one's English, right? So what's our initial and final? Initial would be the water on top, or more than initial, final, it's 1 and 2 would be more appropriate, right? 1 and 2. So 1 would be at the surface and 2 would be right when the water's jetting out. So what's the pressure? Pressure on top when interacting with air, that is just atmospheric pressure, so that's going to be P atmosphere plus half rho v squared. Now the water is not actually jetting out anywhere, so it has no velocity up here, so this is 0, plus rho gh. So I'm going to say rho g. Now when I need to put a height, for convenience I could make this my 0 height, so that the height at which the water is on the top is 6 centimeters or 0.06 meters. So this would be 0.06 equals pressure when the water is jetting out from here. That's the same pressure because it's interacting with air. Or air is exerting a pressure on it, which is again atmospheric pressure, plus the velocity with which it's jetting out, which is what we're looking for, plus density times g times height. Now I made this my 0 height for convenience, and this is where it became convenient. That is 0 now. This and this are the same, so I can cancel them out. So I get, and then I have rho on both sides, so I'm going to even go ahead and cancel the rho's out, because if I divide both sides by density, they go away, right? So I'm left with g times 0.06 equals half v squared, or v squared equals 2g times 0.06, or v equals square root of 2 times g times 0.06. And that should give me something like, what should that give me? That should give me I'm not actually completely sure. Just go ahead and plug it in. I had it written down somewhere, but I can't see it now. So go ahead and plug it in, and you should find the right answer. I should get back